we're back. Welcome back and happy Tuesday. Today, we will continue on with our discussion of the transport layer. Specifically, we'll look at the behaviors that the sender and receiver endpoints in the transport layer engage in order to enable this reliable data transport. But before we begin, some administrative bits. Homework number 2 is due this Thursday, the 25th of February, at the usual 11:59 and 59 seconds. That's 1 second before the stroke of midnight. Why don't we begin? Where we last left off, we talked about the checksum and we gave an example for two 16-bit integers. We went over the different scenarios for adding two binary digits with a carry and without a carry. We did that for two 16-bit integers in computing the checksum, and then if we had a carry out from the result of this sum, we added it back into the least significant bit. The result was our sum. We compute the checksum, which is the ones complement of that sum, including the carry. All right, so why don't we begin with substantive material? So let's look at principles of reliable data transfer. Now, with this, in the book, they do a fantastic job. And this reliability is one of the top 10 most important concepts in computer networking. Now, in this, you have the seam between the application layer and the transport layer. We have the application layer above, and we have the transport layer here down below. Now, for the sending process, when we have our message in the application layer, it sends its message through a socket API call, and it takes its data from the application layer and it puts it into what it perceives as a reliable channel. That data emerges on the receiver endpoint transport layer and is delivered to the receiving process up above the transport layer on the receiver endpoint in this communication. So this is the service that's provided. Now, of course, the applications view a reliable channel, but that's not the case in practice. The transport layer sits on top of the network layer, and the transport layer, when it gets that data from the application layer above, the application perceives that it's doing a reliable data transport send. So we call that RDT send, and that's in the book. And when the data arrives at the transport layer endpoint in this communication on the receiver side, a deliver data method is called. And so that takes this data that emerges on the receiver endpoint and it sends that message data up into the receiving process. Now, underneath the covers, the transport layer, which is in the center here, it communicates with the network layer. And so here's the network layer down below, here's the transport layer in the middle, and here's the application layer up above. And so we direct your attention to the seam between the transport layer and the network layer. That's an unreliable connection. Now, this reliability is implemented by the runtime behavior of the transport layer. But when you send that segment into the network layer tries the best it can, but no guarantee, but it tries the best it can to get that segment to the other side. And so from the perspective of the transport layer, it uses the services absolutely of the network layer below, and it perceives it as an unreliable data transport or a UDT send. So this transport layer, it gives the illusion of reliability, but it interfaces with this unreliable transport, namely the network layer. And so the transport layer perceives below, through the seam it shares with the network layer, it perceives an unreliable channel. And so the transport layer uses this unreliable channel afforded by the network layer, plus its protocol implementation in its runtime in order to achieve this reliability. And so this unreliable channel has a non-zero probability that eventually the datagram at the network layer makes its way across the network. And what we'll see, if you retry sending again and again and again enough times, eventually with a non-zero probability over this unreliable channel to send successfully this datagram across the wire, with a non-zero probability, eventually it will get through if you try it enough times. And so the transport layer uses an unreliable data transport send, or UDT send, over the unreliable channel, trying to get its segment to the destination transport layer endpoint. And so on the transport layer endpoint for the receiver side in this point-to-point communication, we have an RDT receive that occurs, and that's the delivery of this datagram and the unwrapping of the segment inside of this datagram and sending it to the transport layer, this RDT receive, at the endpoint, the receiver endpoint in this communication. And so the characteristics associated with the unreliable channel are going to determine how complex this RDT protocol, reliable data transport, is, this runtime behavior in which the transport layer endpoints engage. And so in the book, we have the sender side on the left, and we have the receiver side. And it's important to note that when we're talking about data going from a machine on the left and a machine on the right, the machine on the left is the sender, machine on the right is the receiver. When we're talking about data going from the machine on the right to the machine on the left, the machine on the right is the sender, and the machine on the left is the receiver. And so with this, we're just talking about the sender role and the receiver role as it pertains to the endpoints in the communication. And that communication can be bidirectional, but in this case, we're only talking about the sender role and the receiver role. Those roles swap when we deal with a communication that goes from machine A to machine B, or machine B back to machine A. Okay, so in this diagram, we have a reliable data transfer protocol on the sender side for the transport layer on the sender side, and reliable data protocol, RDT, on the receiver side. And so we have an RDT send, which is called from above by the application, and it passes its message data to the transport layer, and this data is to be received by the receiving process on the receiver side endpoint in its application layer. And so we also have UDT send from below. This is called by the reliable data transport runtime, or implementation, on the sender side, and it's used to transfer a packet over this unreliable channel upon which the transport layer sits, namely the network layer. Likewise, we have RDT receive, which is called when a packet arrives on the receiver side in this communication, the receiver side transport layer in this end-to-end communication. And then lastly, we have deliver data, which is called by this reliable data transport on the receiver side in order to deliver that message data ultimately to the process which is associated with a port number in a particular socket. And that's the receiver application that it delivers that message data to. All right, so now let's take a look at how we describe these reliable data transport protocols. And so the book takes an incremental approach using a finite state machine, and it develops incrementally the sender and receiver side behaviors for reliable data transfer. And of course, given a finite state machine, you could very easily implement this yourself. And if you were to go into, for example, Linux source code for the TCP/IP stack implementation, you're going to find finite state machine corresponding to TCP behavior, transport layer for the internet stack. And so here we're only going to consider unidirectional transfer. Of course, the sender and receiver roles are going to change, as I said before, when you're talking about directional changes, i.e. the message from a server back to a client versus a client to the server. And we use finite state machines to represent this. And so a state represents a unique condition in the runtime, and we transition between states using these edges. And these edges are annotated or decorated in the following fashion. And so we have one event above a line, that's the state that causes the transition, and then another set of events below a line, and that's the set of actions that are taken when the transition occurs. And so you have a transition from state 1 to state 2 when a certain event occurs, and then you have actions that are taken when this event fires or is detected. All right, so let's take a look at the first example, the most simple example, RDT 1.0, which corresponds to an underlying quote-unquote unreliable channel that is perfectly reliable. That's the simplest case, because if an underlying channel is reliable, every time you send a message into the channel, it's going to come across, and there's not going to be much recovery or many error states that you have to detect and respond to. And so in this, we have no bit errors for the underlying channel, and you also have no loss of packets. And we're going to have separate finite state machines for the sender and receiver. So the sender will send data into the underlying channel. That's the transmission layer on the sender side. And the receiver is going to receive data from the underlying channel. So let's take a look at the sender and receiver behavior. We start out and we wait for a call from above. So that's going to be a socket send for the application on the sender side. And we have the sender here on the left and the receiver on the right. So RDT send is called. So the message data from the application, someone does a socket send, RDT send from above is the event that occurs. So we take this transition, the self transition. So what do? We take this data, make a packet, and then we do an unreliable data transport send, UDT send, of this packet. Now again, because there are no bit errors in this simplistic version of the underlying channel and no loss of packets, we know that this UDT send is going to be correct, meaning it will come through this packet and it will not be corrupted, no bit errors, and this packet will get through. So then the receiver is waiting for a call from below. It's waiting for some incoming packet to arrive from the network layer below. Because remember, this is the transport layer's behavior. So RDT receive, packet arrives, it's delivered from the network layer above on the receiver side, and that's the event that occurs. Okay. So then it extracts the data, message data from the packet that came in, and then it delivers that data to the application above, and then it waits for another call from below. And so this keeps happening again and again and again. It's fairly simple. We have one state each for the sender and receiver. So now we're going to make the underlying unreliable channel more and more complex. We're going to introduce bit errors, and this will give rise to RDT 2.0, the second version of our reliable data transport behavior as described by Finite State Machine. And so here we say the underlying channel can flip bits in the packet. And recall when we talked about the checksum, we said we calculate a checksum and include it as payload in the packet, and then we compare on the receiver side the calculated checksum with the stored checksum that was in the packet. And if they were the same, there's no error. If they are different, there was an error. And so the question then we ask is, if you detect that there's an error in a packet coming across the wire, what do? Well, in human conversation, like on the phone, you say, "Excuse me, can you say that again?" And so that "can you say that again" is called an acknowledgement. You either explicitly tell the sender as a receiver, "Hey, I received this successfully." Is usually what you say in the phone conversation or something like that. Or a negative acknowledgement. Can you say that again? And so the receiver explicitly, with a NAC, negative acknowledgement, tells the sender that a packet had some errors. Now, of course, you as the sender, if you receive an ACK, you just continue. If you receive a NAC, then you retransmit your data. You say it again. And so new mechanisms that you need to implement RDT 2.0 includes error detection and also this idea of feedback, the ACKs and the NAC messages that go in the reverse direction from the receiver back to the sender. And so these are the two finite state machines. And you notice here we have more states for the sender because we have to detect those error conditions. And so here we start out with the sender on the left. Let's look at the operation. We start out, wait for a call from above. We get the RDT send, and we start out for the call from below from the receiver. We get the RDT send for the sender, so we get a message socket send call from the application layer above. And so in response, we make a packet, and we include the checksum with that data when we make the packet. Then we call UDT send, unreliable send. And when we call this unreliable send, we then transition in the sender, waiting for an acknowledgement or a NAC from below. So we're waiting for feedback after we send to look at the result of our send. Did the receiver get it, or did this receiver have some issues with what we sent? So now, on the receiver side, the receiver has been waiting for a call from below. It calls RDT receive. That means it was received. And let's say in the non-error case, it was not corrupt. So that means the stored checksum and the calculated checksum were equal to one another. So in response to that, it extracts the packet that it received, extracts that data, and then delivers that data to the application layer above, and then sends back over the unreliable channel the acknowledgement, so UDT send of an ACK message. And so we send this ACK message, and this ACK message is received back at the sender. So the sender transitions, because RDT receive, yes, and it is an ACK, receive the packet, so it makes that transition back to waiting for a call from above. And so let's take a look at this scenario when we have an error. Again, we wait for a call from above on the sender side, and then we wait for a call from below on the receiver side. So let's do this. We get the RDT send, so someone has called socket send in the application layer above on the sender side. We make the packet, including the checksum, and then we do UDT send on the unreliable channel. And then the sender transitions to waiting for an ACK or NACK as feedback from the sender, from the receiver. And so now the receiver gets this RDT receive, yeah, that's because it got the packet, and it checks to see if it were corrupt. And if it were corrupt, that means the stored checksum is not the same as the calculated checksum, so it does a UDT send of a negative acknowledgement of a NACK. So this UDT send of the NACK comes in, and the event that is detected at the sender, RDT receive, yeah, okay, gets that received packet, and it is a NACK. So what does it do? It resends that packet that it created from before. There's another UDT sent. So this UDC sent is called, and that duplicate of the packet is sent across the wire. And let's assume that one is not corrupt. RDT receive is called from the receiver, and it checks the stored checksum with the calculated checksum. It finds that they are the same, so there's no corruption. It extracts the packet, delivers the data, and then does a UDT send of an ACK as feedback back to the sender. And so this ACK comes back to the sender, and we get a different transition edge because it's a different event for this wait for ACK or NACK. So we get the RDT receive of the packet. It is an acknowledgement, and it transitions back to waiting for a call from above. And this continues again and again and again. And it's because the unreliable channel has a probability that's non-zero for which this packet gets across successfully, that as long as you retry to send enough times, eventually that packet gets through. All right, but RDT 2.0 has a flaw. We're not quite done yet. And so we said that you can have corruption. Now, if you can have corruption in the message on the forward path from the sender to the receiver, that means you can also have corruption in the acknowledgments, the feedback that goes from the receiver back to the sender. So what happens then if your ACK and NACK get corrupted? If that occurs, the sender doesn't know what's going on at the receiver. It doesn't know if the receiver has gotten the message correctly or not gotten the message correctly. That feedback is missing. So it can't just retransmit possible duplicate. So how do you handle duplicates in general? If you retransmit, you're going to get duplicates at the receiver. And so what you can do to handle these duplicates is that the sender can retransmit a packet if the ACK or NACK is corrupted. And then now you stamp each packet with a so-called sequence number, and the receiver then discards any duplicate packets. It doesn't deliver packets that are duplicate because you don't want to get two video frames for the same movie. That would look weird. And so what these sequence numbers encode is which particular packet the sender is expecting to get back. So the sender sends one packet and then waits for the receiver to respond to that packet. So let's take a look at the sender behavior, assuming that the ACKs can get garbled, that they can be corrupted. Now, one of the observations here is that you'll notice we went from 2 states to 4 states because now we have more error conditions that we need to check. So when we look at this, RDT 2.1, the sender then includes states to handle these corrupted ACKs and NACKs. So we start out waiting for a call from above, and that's our state 0, and that's our start state in the finite state machine. We get the event RDT sent from above, so we send message data. We create a packet. We include the data and the checksum, but we also include this sequence number 0. And then we call unreliable send, UDT send, to send it across the wire through the network layer interface that's seen between the transport layer and the network layer. And so now we wait for an ACK or NACK for that particular packet stamp with 0. So a number of things can happen. Either you get the ACK or it's corrupted. And so here we have RDT receive, you get the packet, and if it's corrupt, well, what do? You resend, UDT send. So you resend a copy of that packet if it's corrupt. If you receive it and it is a NACK message, okay, the receiver didn't get the packet, so you do a UDT send. The other condition is this other edge that transitions to wait for call 1 from above. That corresponds to getting the acknowledgement. So you have the event RDT received, so you get that packet. It's not corrupt, so that means the stored checksum and the calculated checksum are equal to one another, and you find that it is an ACK. So you transition now, waiting for a call for packet stamp 1 from above. So now RDT send is called again. So some message, some application is calling socket send with its message data, and you make the packet with the data, compute the checksum, include that, and also stamp that with sequence number 1. And then you do a UDT send on that packet stamped with sequence number 1. You transition to waiting for acknowledgement or negative acknowledgement for that packet stamped with sequence number 1. So you do the RDT receive, that's a self edge. You get a packet. If it's corrupt, then you do a resend of that packet stamped with sequence number 1. If you receive a packet and it's a NACK, you also resend that packet that you created stamped with sequence number 1. You transition only if you successfully get that feedback that says the receiver successfully received that packet, and you do an RDT receive, that's the event, and it's not corrupt, so that means the stored checksum and the calculated checksum are the same, and it's an acknowledgement. Well, there's no action, but you transition now to waiting for the next call from above. And so you start out, you send the packet stamped with 0, and then you wait for ACK or NACK, and then you transition to another send stamp at 1, and so you're alternating between sequence number 0 and sequence number 1. And so this is the receiver behavior for RDT 2.1. We start out in our start state, and you're waiting for the packet stamp 0 from below. Now let's assume that you get an RDT receive, and someone calls socket send from above. It's not corrupt, okay? That means you get some RDT receive from below. You get a non-corrupt packet, and let's say it has sequence number 0. Now, of course, if it has sequence number 0, that's what you were expecting to get, right? So you got packet stamp sequence number 0. What are the things that could happen? Well, you get a packet, RDT receive, incoming as a receiver. It's corrupt. If it's corrupt, you create a NACK packet, negative acknowledgement with a checksum, and you send it. The other alternative is you don't get packet stamped with 0, you get packet stamped with 1. So you RDT receive, let's say it's not corrupt, and it has sequence number 1. So what do? You make a packet, an ACK packet, and you say, okay, well, I'm going to acknowledge it because if I'm waiting for 0, that means it must not have gotten the acknowledgement for 1. So I'm just going to make a packet to ACK that and do the UDT send. So now this transition to get to the next state, wait for 1 from below by the receiver, that's when you receive the packet. It's not corrupt, and it has sequence number 0. So what do? You extract the data, and you notice here, you deliver the data. You deliver the data, so the application layer above on the receiver side endpoint in this communication gets that message data. You make the ACK with a checksum to detect if it gets corrupted, and you do the UDT send, this unreliable send, to get this feedback back to the sender. So now you transition to waiting for packet stamp with 1 from below. Now that you got 0, now you're waiting for 1. So what conditions can you have? Well, either you get out of order, sequence number 0, or you get something that's corrupt. So let's look at the corruption case. You receive a packet, it's corrupt. That means the stored checksum and the calculated checksum are not the same. You create your NACK packet with the checksum, and then you do the unreliable send, UDT send, back across the wire as feedback to the sender. And then you're still waiting back for packet stamp with sequence number 1 from below. Likewise, you can get an out-of-order packet. So here you do RDT receive, it's not corrupt, and it has sequence number 0. Well, you're waiting for 1, not 0. So what do? You construct an ACK, because the sender must not have gotten the ACK, and then you do an UDT send. And you notice here, you do not deliver for this self-edge. Then you get the appropriate sequence number 1. So you do the receive, that's the event that occurs, it's not corrupt. The stored checksum and the calculated checksum are the same, and it has sequence number 1 is appropriate. So then you extract, and the difference is here, you deliver this packet. Then you create the ACK with the appropriate checksum and send it back across the wire as feedback to the sender. Okay, and then this process continues. So here for RDT 2.1, you add sequence numbers to packets, and at the receiver side, it tells you which particular packet you're expecting to receive and therefore deliver. And so 2 sequence numbers is sufficient because you do not proceed in delivering that packet unless it's the correct sequence number you're expecting to get. And you alternate from 0 to 1 to 0 to 1 to 0 to 1 continually. And so you have to check if the ACK and NACK is corrupted. And you have twice as many states on the sender side because you have to remember which packet you're expecting. The receiver, on the other hand, has to check if the received packet is a duplicate or not. And the state indicates whether it's a 0 or 1, what sequence number you're expecting to receive. Now, note, it's really important that the receiver can't know if its last ACK or NACK was received correctly at the sender. It doesn't know that. It just responds to what it gets. So it doesn't know that the sender didn't get the ACK or NACK. All it sees is a sequence number that it wasn't anticipating. And so let's expand on RDT 2.1 and define RDT 2.2, and this is a so-called NACK-free protocol. It's the same function as RDT 2.1, but we're going to use ACKs only and just eliminate NACKs altogether. And instead of a NACK, what we're going to do is the receiver is going to send an ACK for the last packet it successfully received. So it's saying, hey, sender, this is the last thing I got that was successfully received. So the receiver has to then explicitly, with RDT 2.2, explicitly include the sequence number associated with the packet that is being ACKed. And in doing so, it's telling through feedback to the sender, this is what I most recently successfully received. And so if you get a duplicate acknowledgement at the sender, that's the same action that is taken as if it got a NACK, that is to retransmit. So it says, oh, you told me the second time that you received a certain packet. You must not have gotten the next one I sent, so I'm going to retransmit. So this is RDT 2.2, and this is the sender fragment. And then what we'll do is talk about the receiver fragment, and this is going to be replicated about this diagonal. And so you can imagine then, over here, we're going to have a state called wait for call 1 from above, and then down below, we're going to have a state called wait for ACK 1, right? And so it's the same as this upper fragment, replicated, but instead of saying 0, we're going to say 1 for those other half of this fragment. So here we have our start state. We wait for a call 0 from above. An application calls the socket send, so it's RDT send with the message data. We create a packet, and remember this is the sender side, and we stamp it with sequence number 0. Here's our data, and we include the checksum. Then we call UDT send with this packet we just created, and then we're waiting for acknowledgement for packet stamped with sequence number 0. So we sent packet with sequence 0, and now we're waiting for the ACK for 0. So one of the things that can happen, it can either be corrupt, or we get an acknowledgement for something that's not sequence number 0. And so here, RDT receive, if it's corrupt, well, we do the UDT send. We're resending this packet stamped with sequence number 0. If it's received, RDT receive, and it's the wrong sequence number, it's sequence number 1, we also do a UDT send. And so this is ACK of packet stamped with sequence number 1, and UDT send is similar to receiving a NACK in RDT 2.1. And so RDT 2.2 is called a NACK-free protocol because we eliminate NACKs and we include sequence numbers and the detection of the duplicate of the sequence numbers as a way of equivalently stating negative acknowledgement. And so let's take a look at the other transition edge out of wait for ACK0. We get RDT receive, so we get that packet. It's not corrupt, so the stored checksum and the calculated checksum are equal. And it is the acknowledgement for packet stamped with sequence number 0. So we transition from wait for ACK0 to wait for call 1 from above. And so this wait for call 1 from above is exactly like wait for call 0 from above, only instead of 0, it's 1. And then we also then transition to wait for ACK1. And wait for ACK1 looks just like wait for ACK0, except that instead of saying sequence number 1 here, we'd say sequence number 0 in this is ACK. And then here for this edge corresponding to that lower state that's not drawn, instead of saying is ACK0, we'd say is ACK1 to transition to wait for call 0 from above. Okay, so that's the sender side of RDT 2.2. Let's take a look at the receiver side finite state machine for RDT 2.2. Now, of course, with this receiver side, we start and let's look at wait for 0 from below. And so here we have a self edge, and that self edge corresponds to two conditions. Either we have corruption or we have an out of order packet, or the sequence number is not what we expected. So here we RDT receive from above. We check if it's corrupt. If it's corrupt, that means the stored checksum and the calculated checksum are not the same. We do a UDT send, unreliable send. So we're resending the acknowledgement from the receiver, the acknowledgement that was most recently created. And so if we receive, RDT receive, and it's the wrong sequence number 1, we also resend the acknowledgement. In that case, it's the acknowledgement for packet number 1 that we just created. And so now for this edge, that means we get an RDT receive, and it's not corrupt. The stored checksum is equal to the calculated checksum, and it has sequence number 0. And so now we transition to this other state, and it's wait for 1 from below. Now, of course, we're going to have a self edge, and that self edge is going to look just like the self edge here, except instead of having has sequence number 1, it's going to say has sequence number 0 on the packet. And so then when we look at this edge to go across transitioning to wait for 0 from below, well, that's the case where you receive the packet, it's not corrupt, and it appropriately has sequence number 1. So what do? Extract the packet, and we deliver the data, and then we make the acknowledgement for it with a checksum, and we send that across the channel. Okay, and so we'll note that for this edge to get from wait from 0 from below to wait for 1 from below, we're going to deliver the data for that packet with sequence number 0 to the application layer above. So these are just fragments. We would repeat these second time as half of the states for each one of these finite state machines for the sender and for the receiver. Okay, so now we're going to add this idea of loss, not just corruption. And the new assumption is more realistic to what a modern network is. The underlying channel, not only can it corrupt packets, but it can also lose packets. And so because it can lose packets, this means it can lose the data on the forward path from the sender to receiver. It can also lose the ACKs on the reverse path from the receiver back to the sender. And of course, we talked about this loss can happen if this packet meets a router that has run out of buffer space, that packet gets dropped. And so we have a checksum, we have sequence numbers, we have ACKs, and we have retransmissions. Those can help, but it's not quite enough in this case of packet loss. Now, the approach that it takes to deal with this last version of RDT, RDT 3.0, when we have loss, is to wait a reasonable amount of time at the sender in order for an ACK to be received. And so after that timer fires, what happens? After that timer fires, you retransmit. And so now we have another condition that can trigger the retransmission. The retransmission can also occur if it's taking too long between when we sent it and we receive an ACK. And so a packet could just be delayed and not necessarily lost. So that means retransmissions by the sender will result in duplicates, and we need to handle that at the receiver. And so we require a countdown timer in order to detect these losses. So this is the RDT 3.0 sender. Now this RDT 3.0 sender will start with wait for call 0 from above. If you receive a duplicate RDT receive, you just eat that packet, you don't deliver. So you have this RDT send from above, you create a packet with a sequence number 0, is your data, and a checksum. You do the UDT, unreliable send, and you start a timer associated with that packet. And you transition to waiting for the acknowledgement for what you just sent from the sender perspective. So now there are 3 different alternatives. You can have the corruption case or acknowledgement of the wrong sequence number. You can have a timeout, or you can actually get this packet stamped with a 0, the ACK for it. So now you're waiting for an ACK 0. So the first case, you get a receive, you receive a packet, RDT receive, and it's corrupt, you do nothing. If you receive RDT receive and it's an acknowledgement for the wrong packet for sequence number 1, you do nothing. If the timeout expires, it's taking too long to get an acknowledgement, you resend that packet that you just created, another UDT send of that packet stamped with sequence number 0. You hold on to that packet, and then you restart the timer. So then, ultimately, you resend enough times. Eventually, one gets through, you get the ACK, it comes back, and then you get the RDT receive. It's not corrupt, so the stored checksum and the calculated checksum match. It's a correct acknowledgement. See, for sequence number 0, you stop the timer, and then you're now waiting for call for packet number 1 from above. All the while, if you get a duplicate ACK, you just throw it away, RDT receive, and you don't care about it. Now you're waiting for the call from above. So someone calls a socket send again, an application, RDT send with that data. You send the packet stamped with sequence number 1 with the data and the checksum. Do the unreliable send and start the timer for that packet with sequence number 1. Now you're waiting for the acknowledgement for packets sequence number 1. And of course, again, we get those 3 conditions. Here, RDT receive, it's corrupt. So the stored checksum and the calculated checksum do not match up. And it's acknowledgement for the wrong packet for sequence number 0, you throw it away, you don't do anything. The timer fires, meaning it took too long to get an acknowledgement. What do? You resend that packet stamped with sequence number 1 and restart the timer. So then you get your packet, RDT receive, from below. You find it's not corrupt, so the stored checksum and the calculated checksum are the same. It is the correct ACK for packet stamped with sequence number 1, so you stop the timer. And now you transition the sender to waiting for the call 0 from above, and this process repeats itself. So the receiver is the same, and this is all in the book. They do a fantastic job about it. Let's look at RDT 3.0 in action in the form of a protocol diagram. And so here we have the sender on the left-hand column, the receiver on the right-hand column, and this first case talks about no loss. So you send a packet, and send it to the receiver. Receiver gets that packet stamped with sequence 0, and then sends back the ACK. The sender receives that ACK 0, and so it now sends packet 1. The receiver gets packet 1, sends ACK 1. The sender gets ACK 1, switches to sequence 0, sends that packet, sends packet 0. Receiver gets packet 0, delivers it, sends the ACK, sends back ACK 0. So that's the no loss case. Let's look at what happens with packet loss. So the sender sends packet 0. The receiver gets packet 0, sends the ACK for 0. That ACK comes back across to the sender. So then the sender sends packet 1, and that packet 1 is lost. So what happens? The sender has waited some amount of time for the ACK for packet 1 to occur. The timeout fires, and then it resends packet 1. So it resends packet 1, that gets through. Receiver gets packet 1, sends ACK 1. The sender receives ACK 1, sends packet 0. Packet 0 goes across the wire, receiver gets it, sends back ACK 0, and this process continues. And so here we see the timeout fire on the sender side, and that triggers the resend of packet 1 because the sender hadn't received the ACK for 1 in a long time. So it assumed it was lost, and it resent. So this is the loss of an ACK. And loss of an ACK can also occur. ACK is just a packet, and you can get packet loss for the forward send message. You can also get packet loss for the ACK in the reverse direction. So you start out, and the sender sends packet 0. The receiver receives packet 0 and sends ACK 0. So there's that first round trip. ACK0 comes in, sender gets it. Now it sends packet 1. Packet 1 goes across the wire, receiver gets it, delivers it to the application layer above, and it sends back to ACK1. ACK1 is lost. So then the sender hasn't received ACK1 in a long time. A timeout expires, and then the sender sends a duplicate of packet 1. So the receiver detects that duplicate. It does not deliver it, but it sends the ACK for packet 1. Now the sender gets ACK of packet 1, and then it switches packet 0, sequence number 0, and it sends packet 0. And then the receiver receives packet 0, sends ACK0. And that's lost ACK. And so from the sender side, because this ACK1 did not get back in a timely fashion, the sender assumed that either the packet was lost or the ACK was lost. Timer fires and it resends packet 1. On the receiver side, it got 2 copies of packet 1. It detected the duplicate and did not deliver it, sent the ACK for it. Okay. So let's take a look at a delayed ACK, a premature timeout. So the packet was not lost, it's just taking a really long time to get back to the sender. So we have this scenario again. We send packet 0. Packet 0 gets to the receiver, and the ACK0 comes back. So now the sender sends packet 1. And packet 1 gets to the receiver. It delivers it to the application layer above, and then it sends ACK1. Now, of course, ACK1, maybe there's a lot of congestion. It takes a long time because of queuing delay. It takes a long time to get back to the sender. In the meantime, the timer fires, and it resends packet 1. So it resends packet 1, and while packet 1 is in flight, the ACK1 arrives at the sender. On the receiver side, well, it got a duplicate copy of packet 1. It detected this duplicate and did not deliver it. It delivered it to the application layer above the first time it got packet 1, but not the second time, because it was no longer expecting to see packet with sequence number 1. So it was a duplicate packet that the receiver got at this juncture, and it did not deliver it. It detected that duplicate. But what it did do is it said, let me send an ACK for packet 1 because you must not have gotten the ACK that I sent you. So in the meantime, what happens? That delayed ACK finally arrives. The timeout fired, sent the duplicate. That duplicate was ignored. It sent an ACK1. So it got that first ACK1, it sent packet 0. So the sender continued forward, sending the packet with the next sequence number 0. So after that duplicate ACK was sent by the receiver, packet 0 arrives, and then the receiver sends the ACK for packet 0. And so this received ACK, well, when it got that first duplicate ACK for ACK1, it went ahead to go to packet 0. But when it got that second ACK1, it just ignored it. And it said, oh, well, you know what? Let me resend packet 0 because that means you might not have gotten packet 0 since you're sending a duplicate of ACK1 and not ACK0. And so then, eventually, as packet 0 is resent, the duplicate send of the packet on the sender side, this ACK0 finally gets back. And now, once this ACK0 gets back, the sender knows that packet 0 was successfully received. And so on this receiver side, this duplicate packet 0, it was not delivered, sends another ACK0. But then on this second ACK0, there's the first, here's the second, it's a duplicate ACK0. The sender just ignores that and then moves forward with packet number 1 for the RDT send from above. And so eventually, on the sender side, it ignores the duplicate ACK. On the receiver side, it ignores the duplicate packet, and then they sync up with one another eventually. All right. So these are the 4 scenarios of RDT 3.0 in action. Now, RDT 3.0 is correct. It gives you reliable, in-order delivery, responding to lost data as well as corrupted data, both for the forward message, the packet, as well as the feedback, the ACKs. So it's correct, but the performance is absolutely horrible. Let's imagine you have a 1 gigabit per second link, and you have 15 millisecond propagation delay. And let's assume, for the sake of argument, this is in the book, you have an 8,000-bit packet. So if we were to look at the transmission delay, that's L, that size 8,000 bits, over R, that's 1 gigabit per second, so it's 10 to the 9 bits per second. That's 8 microseconds. And so the transmission to delay, or time actually sending that data, is 8 microseconds. If we were to look at utilization, that's the fraction of time over which the sender is actually performing the send of the data. And so if we look at this, we have the utilization is just the amount of time it spends for the transmission. That's 8 microseconds over the round trip time plus L over R, our transmission. And so if the round trip time is 30 milliseconds, that means that every 30 milliseconds, we're sending a 1 kilobyte packet, or 8,000 bits, every 30 milliseconds, if we have a 30 millisecond round trip time. So that's 0.008 over 30.008, which is an absolutely minuscule utilization. That utilization is 0.027%, which is absolutely horrible. We have this gigabit per second link, but we're not really using the bandwidth of this gigabit per second link. Now, of course, this is an issue with RDP 3.0 that we will rectify by sending more than one packet per round trip time versus so-called stop and wait, where we send a packet, wait for it to be acknowledged, and then send a packet and wait for it to be acknowledged. So we'll extend this RDP 3.0 behavior with the ability to maintain more than one packet in flight and not just wait for packets one at a time to be acknowledged before moving forward. Okay, so with that, we will end there, and we'll pick back up next time with so-called pipeline versions of RDP 3.0. And so we'll end there, and as usual, please stay healthy,